Hello and welcome everyone. Today we'll tell you some stories about femtocell hacking. My name is Alexander Zaitsev and this is Alexey Osipov. Basically for now we're totally unemployed researchers and penetration testers. Also we love Cloud a bit. So I think we'll build up it today the following way. I'll try to cover some engineering parts of our research, how it went. And then the second part, Alexey will tell you about kind of business impact of things we discovered. So let's start. Some time ago, during our small project, we totally needed to create our own UMTS network. And as you all may know, there is an open source project, OsmoCombBB. But it's no matter how awesome it is, it's 2G only, and so it couldn't help our goal. Anyhow, so we started to look towards kind of cheap femtocells as a platform to build on. And apparently found why. The Huawei UAP 2105. It's still sold on a number of Chinese sites, no matter that it's officially discontinued. Since the very unboxing, we had some promising feelings about what awaits us. Though, turns out that the path to our goal wasn't as simple as we wanted to be, and actually it's still away. So we tried to look into it kind of deeper and found out, after looking for the publicly available interface, we found only a web interface, HTTP one. We disassembled it and found out that the board consisted of two boards. One, the main board, and the radio board. So one thing attracted our attention. It was a 26-pin header sticking out of the main board, and we thought we could get some interesting stuff out there. Why no? 26 pins could be a lot of fun. Some debug interfaces, especially when it says kind of debug near it. So to keep things cheap and simple, we took our Arduino Duo because it's 3.3 volts, so we don't fry anything, and started to poke all the pins, sending data to one of them and receiving another, trying to find some correlations, and eventually we found a dependency. Our observation showed that two of the pins consequently responded. We eventually found out that this is UART pins, TX and RX, so this was kind of easy. We discovered that there's VxWorks there by connecting with our serial adapter. VxWorks has attracted quite a bit of attention in recent years in the security community. So it was kind of interesting things for us. We found out the CPU, the kernel version, flash volume, and the fact that it's going to boot to flash. So how did it go? The board, after boot up, was waiting for a key press, and if it didn't receive a key press on the UART interface, it booted to a normal mode, to the main software, which we call the blue pill mode, where everything is as usual. It's your kind of ordinary world, and it's an ordinary web interface you saw previously. Opposite, if we interrupted the boot up process by pressing a key, we dropped into some kind of VxWorks shell. We called it a red pill mode, in which you can definitely stare at the matrix as long as you like, discovering all kinds of things. So again, about the blue pill mode, it's just a plain web interface. So just configuration interface for the consumer. Kind of boring. opposite the red pill mode looked kind of interesting to us. We found out that it exposed some debug capabilities, even a C interpreter, full-blown flash file system access, and basic networking support. One by one, the debug subsystem, it even has good help in here. So it has all the things you need to debug your mirror-looking glass code for VxWorks. It has breakpoints, step, stack trace, disaster, all kinds of things. More than that, it can even manage some running tasks, quite convenient. Can do memory dumps, memory edits, register manipulation, and it even had a debug symbols compiled into it. So it all was there for us. Lucky. One of the most interesting things we found is that the shell itself, the interactive shell, was in fact a kind of C interpreter. So you could write a C code and execute it line by line, right in place. So to test it, we wrote some code to test the functionality, and now try to show a demo how it worked for us. Yeah. So here we're connecting to this device, getting the shell prompt, checking the version, and then just copy pasting our kind of C code, creating the SOC address structure and the memory of VxWorks. We bind it to our IP address on the port. It's okay. Now we open our cat listener. And then we just issue 4 commands to connect and write some data into it. Checking back. So here is it. It executed. It says hello, Black Hat USA. So it's kind of working. Kind of nice functionality for a shell to just code and plan C and execute it right away. Continuing. We also had full flash file system access right out of the box. It has all the usual commands to work with the files on the file system, list directories, change directories, even recursive listing, which you can see on the right. You can type your files, binary, all the way around. You can see in the left down corner a fragment of the main configuration file. You have CFG XML, which stores all the critical configuration settings for this femtocell. As if it wasn't already enough, these guys also left us some networking capabilities. So we could transfer files back and forth via FTP and remote shell. So awesome. After that, we started looking for what's running actually on this board. We found at least 3 interesting tasks, self-explanatory, the telnet, the FTP server, and WDB RPC interface. The last task with the red line you see down, it's a task which actually boots up the main software for the blue pill mode. If we resume execution of it, it will just go first and resume to the normal function of it. Red pill mode again, yeah? These services are really running. Nmap shows us all of them, but there's a problem. When we issue the resume to boot to app process or reboot our device, we cannot see this anymore. So we wanted to do, how to work with this kind of forward. First place we wanted to get rid of all these pesky wires and UART stuff. We made an assumption that during the boot up, the system actually had this service started before it jumped over the blue pill mode. So we tried to spam it with our simple Python code, trying to connect to the telnet and issue some commands to stop the boot into main application. And on the right, you can see the log of this. Actually, it's working. Twice connect, timeout. It's still booting, wind it out. And then you can see the task stopped. And task table, which after which we just disconnect our script and can connect to the 23 port of telnet server and throw away all these wires and close the board. Work convenience via the telnet. So to continue our research, we needed to get the main, the code of the main software, the blue pill code. Actually, there are a lot of ways to do this. The most obvious by time is just to dump it all with the D comments after the firmware of the blue pill unpacks and then parse it. But it's kind of not really convenient, slow. We've also remembered that there was WDBRPC there, which is kind of famous stuff due to awesome HD Moore research and his Metasploit model, which main capability is dumping the whole memory via this means. So it was the things we tested, and it worked out really well. It gave us really fast binary output, ready all the right sides. It calculates all itself, and just ready to go for analysis. It would be even more awesome if someone could write an actual debugger using these capabilities we have in Ruby files out there in Metasploit, the read memory and write memory and so on, but it's somewhere out there. So this time we came to our IDE Pro, finally. The best tool so far out for us for complete analysis. As I've already mentioned, we had precompiled debug symbols. We had a symbol table which we needed to correlate with our analyzed code. We did it with a simple Python script, and after which it looks quite fancy. You can see all the symbols. This kind of nifty example, one function which relates to how this device handles its licensing. The licensing actually is this long base 64 string on the down side, which turns out to be encrypted by ACE. And small of our task was to find out how to decrypt it. We did it here using IDE Pro. We found out that there is a static part of key, which is Femtoland wave. And actually, the rest was just last 6 bytes, last 6 characters of so-called API, the unique ID of the device. After that, it was quite simple. It's a binary blob which stores settings yes, no, yes, no. For licensing, it's kind of main configurations of main features, such as data bandwidth, handover capabilities from macrocell to the femtocell, and so on. So, kind of analysis. Actually, we wanted to execute our code in a blue pill mode. Yeah, we didn't want to stay always in this debug interface, the bootloader. And again, it was at least 2 ways to do it. First is long and boring. Yeah. Download the firmware, extract it, patch, pack, upload back, hopes all goes well without any checksums or hashes and so on. And another, as we thought, was quick and dirty. It ended up not to be quick, but still fun. It's just we wanted to try to take over control dynamically as it loads. So for this, we needed some piece of software which could be injected written upon some obviously executed function in the blue pill mode. Yeah, actually we chose the one that handles entering the password for web interface. We've overwritten it with a small awesome snippet that, as you can see, opens a socket, receives some compiled C code on this socket, allocates memory for it, copies it there, and correctly spawns a new task out of there. So when somebody wanted to log into the web interface, it actually spawned the socket. We could dump our code there, it executed, spit everything back. Nice and clean, but it was not quick. Actually, not all femto cells appear to be created equal. During analysis of second batch of these devices, we found out that some of them did not have anything of any one of these interfaces that we've described right now. There wasn't Telnet, no WDB RPC, not even UART. It was kind of sad for us because we wanted to build up on this cheap little platform to continue in research, to give it back to the community to poke on with. And without these interfaces, it was all not worth it. So we tried to think hard whether everything was lost, and the answer was no. Actually, we took one of our last guesses on this 26-pin connector, and in some time, we found out that there was actually a JTAG connector. We did it some kind of poor man's way. We didn't have awesome JTAG by Joe Grant, but we did have our Arduino Duo, which we flashed with JTAG NAM, the open source sketch for the Arduino. Then connected all the pins to all these mega pins of the Arduino Duo. Started brute forcing it, looking for JTAG pins. Unlike the JTAG, it's quite slow process on the Arduino. And nevertheless, after some hours, we got it. And it was a total win. Actually, we checked all our boards, and all these JTAGs are there. So this was the vector we need to follow to achieve this availability of this platform as the cheap one and interesting to build on. So we connected another strange way to the JTAG. We didn't have, again, the right adapter for it. So we used a Raspberry. Here's a map of the pins on Raspberry connected to the JTAG pins on the board. Eventually, with a fresh version of OpenOCD that supports bit banging, you can use your Raspberry Pi as a JTAG adapter. So, here we go. We tried to connect there. We knew this processor we were looking for from this version information and so on was actually the ARM 926 EJ processor. And here we can see that it's not what we expected. So what's wrong with it? What's wrong with OpenOCD maybe? Turns out no. There is another set of pins on the board, actually the jumper pins, with some labels underneath it, two of which said JTAG mode 0 and 1. Turns out that switching these jumpers, we could access different OCD interfaces for different devices. There was 3 on this, and our processor that we were looking for, the R1, was when we set up the jumper to the JTAG mode 1. So, achievement unlocked, yeah? JTAG Redneck. Here is the output of OpenOCD, which connected successfully. And here is your full-blown debugging interface with remote GDB attached to OpenOCD interface. You can dump the registers, modify it, dump memory, modify it, disassemble, whatever step. But wait, we really love IDA. And we thought of the way we could make it more convenient. It was kind of simple from the first look. IDA can connect to remote GDB server, but wait, it shows kind of enable allocate memory, so drop GDB connection. Bad. We tried to Google some of these messages, and actual internets are full of things. It was to the rescue, and we solved this problem with a small patch. Actually, people already dealing with this problem only changed 2 lines of code, some malloc modifications. And we try again, and there it goes. Can't even expect any more of the convenient interface to analyze it on the runtime. It has all of this. All you need is just to dump all this memory. Again, using JTAG, it's more than doable. Then you use a script, the Python script, to correlate your symbol table to the code you are debugging, and you can do whatever. We were kind of glad to see it because it restored our faith that with such capabilities we could modify control flow in any way we like to, for example, just refresh it with the firmware we liked from our first femtocell. So there it goes. And the conclusions for my part, the kind of VxWorks reverse engineering hardware stuff. We've messed with some devices, and not only we, during the last time. And actually, quite a few times we see this real-time OS, the VxWorks, in a lot of telecom devices. Femtocells, USB modems, smartphones, you name it, especially the ones manufactured by Huawei, they like it. There are even sometimes when you think there is no VxWorks, you think there is kind of Linux, you root it, blah, blah, blah. And poking around, you actually understand that underneath it, it's still VxWorks controlling all the radio parts and stuff requiring real-time operation. So the last time, 2 of our close friends and colleagues were working to this on similar research about VxWorks in telecom devices. There's things to see in this presentation from Hack in Paris they gave. We think that due to increasing deployments of, kind of work. Nah. Let me share. Dooba-dooba-doob. Due to its vast deployments on telco devices, we think VxWorks deserve some more thorough and deep research from the community, from all of you guys. There are things to be researched, and there are things to be found. Please go poke with all your devices. Eventually, you'll find a VxWorks out there that you can hack. This was kind of fun part and so on with stupid pictures. Now it's kind of hardcore wizardry from Alexei about our actual telecom findings. So Please welcome Alexei.
Thanks, Alexander. That was hardware part. It was about femtocell inner parts. It's about VxWorks, but actually, femtocells work in large networks. For example, on the screen you can see home node B. It's a femtocell that is connected via internet with a security gateway, which is connected to the HMS, to the HNB, and so on and so on. There are too many different 3GPP abbreviations that will blow your mind, but actually you want to hear it. What is security gateway? It's ordinary VPN. It protects all the connections over untrusted networks. If you're connecting via Wi-Fi, via landed channels, this data is untrusted. And because everything inside the core network is trusted data, you don't want to mess with it. IPsec works in the main mode, so there is no opportunity to get the hash of the password if it was used. And guys from the consortium thought that YAP AKA or YAP SIM is a good way to protect this connection against malware or evil purposes. What is actually YAP SIM or YAP AKA? It's ordinary GSM authentication. You send random data to the SIM card, and it returns to you 52 or 64 bits of the key that is securely made inside the SIM card. You repeat it 3 times to get enough key material, and with this key you can connect with the VPN. On the VPN side, there is ordinary HLRs or storages with the keys, and they do the same things. You encrypt and authenticate every packet, and it's really a secure element. It seems legit, but actually it's based on GSM authentication. You can take the SIM card out of the femtocell and replay every data out of it. So GSM networks are not have no replay protection. So the first part to gain control over the femtocell over the network, we take SIM card out of the terminal, insert it into our SIM reader, and created different pairs of random number and key from the SIM card. And with a piece of software and this data, you actually can connect femtocell to yourself and gain control of sensitive information that is passed through this channel. There is obvious way to do horrible things to connect elsewhere, not connect femtocell to you, but we think that would be not that good. There is a VPN server, well-known VPN server, Strong Swan, that has different flavors of EAP. And one of these variants is EAP SIM file. You create this data, you create triplets of encrypted data, and substitute it into Strong Swan. And actually, there is a configuration for such a thing. You can connect most of the femtocells that are based on EAP SIM to yourself. But actually, it's small text. The presentation will be made public later, so you can just download it and take this configuration. Inside the tunnel, the things are getting interesting. It's a new field of attack because it's a new interface that is kind of protected. You have new IP address with new open ports. As Alexander already said, there was on the HTTPS port from outside. From the inside, there is different kind of ports. For example, 7547, it's tier 069. There is CTP, there is HNBEP over CTP, there is RUA, there is RUNAP, there is DTAP, there is different kind of things. But to manage all these interfaces, you need management server. It's called HomeNodeB management server. Its protocol is TR, and there are two different parts of it. It's initial HMS that provides basic authentication of the femtocell by the API, and serving HMS that protects femtocell from moving from one place to another by geolocating. Provides configuration of radio part, for example. It provides information about channels. It provides information about scrambling codes and so on. And this HMS server provides access to HNB gateway. It says, okay, I've configured you, so connect to the other server. What are configuration options? There are over 9,000 of them. You can sniff neighbor base stations. You can enable debug interfaces. You can give information about users who are connected to this femtocell. You can gain information about cryptographic keys. You can reconfigure IPsec, and so on and so forth. But there is also not much of interest because we want to create our own network. So we provided IP address of HNB gateway. It's a HomeNodeB gateway. And it's actually just a gateway. Femtocell connects to it with the HTTP protocol, and special header says where in the core network you should send your data. And HTTP gateway only sends it elsewhere because femtocell is already configured, and there is nothing to be done. And when a femtocell connected to this HTTP gateway, from its point of view, it's already in core network. Okay, we connected to femtocell to us. We have different packets that have nice dissectors in Wireshark. Okay, we can receive all packets, accept all requests, and hope everything will be fine. But actually, you can't accept all the requests just like that. There is a HTTP protocol, which is the base for all the connections from the femtocell to the core network. It has kernel module in Linux since a very long time. It has user line bindings to access HTTP with your software. It's widely used in telecoms, but long story short, every 2 or 3 minutes it breaks with no good reason. Maybe it was femtocell, maybe it was my hands, I don't know. After HTTP, there is a HNBEP. It's a protocol that is used for gateway and is pretty simple. It issues requests to register itself in the core network, and you can just accept it. And when the user connects to you, you can accept it as well. After that, our femtocell come to the blue mode without any connection to original telecom hardware or software, and was ready to accept users to it. Well, that was an achievement, but that was not easy. There is different domains inside the telecom network. It's a CS domain. It's it's for voice and SMSs. And PS domain, it's for internet. When when you connect with the phone to your femtocell, it issues location update request, and if you try just to accept it, it will fail. I was very sad about it, and I didn't know what to do. I downloaded specification. It's about 5 DVD disks just with PDFs, with different versions, with different information, with the documents linking to the other documents, these documents linking other ways, and so on. There is plenty to read. But actually, there are a number of documents that are really useful for creating your network. It's TS24008. It's basic core network protocols. It describes pretty much everything about how to connect, how to manage the connection, and how to authenticate. And also it provides information about mutual authentication in 3G networks. There are different buzzwords in news. When they say, oh, 3G networks are protected from the 2G attacks against evil base stations, so IMSI catchers are really impossible. But we found some different things that are manageable inside the normal behavior of the femtocell. For example, we can issue identity requests. It provides you with information about IMCI, IMEI, and so on. This information actually is that information that you use to follow someone over the air. And IMSI identifies SIM card of the subscriber, IMI identifies mobile station of subscriber. So we can create our IMSI catcher that won't terminate calls onto it, but can provide you information about where the person is and what he is doing. So, and the user can be identified by both the SIM card and by his mobile phone. So if you take out your SIM card from your phone, but use the other one, telecom network can also follow you. And when they say that they can't find the stolen mobile phones, don't trust them. There is a nice packet, GMM information. It provides you information about the network you're connecting, for example, in the roaming. You can issue its full name, you can change time zone, for example, if you travel far enough, and different local time. Well, there were interesting talk on the Black Hat Europe last year about bypassing HSTS protection in web browsers. It was based on man-the-middle NTP connections, so the clocks are running faster and HSTS header is blocked. But there are different restrictions. For example, the main one is that all the data is client issued. So you can't just send any information to a arbitrary client. In the UMTS, you have nicer things. You can just send any date in the future, in the past, and the phone will take it without hesitation. And the most interesting part about UMTS that it's not really integrity. There are different opportunities to bypass integrity checks. It's those checks that mutually authenticate mobile phone and base station. According to specification, it's impossible. But with the bad code and bad opportunities to use it, you can do different things. For example, under certain conditions, you can send arbitrary SMSs without authentication on your femtocell or base station. And, for example, you can bypass EMT's integrity checks. I will show a demo with these three vectors. We have our red pill femtocell and our phone. We issue commands to bring it to life, and it switches to blue.
Sorry. Sorry, this is the annotated one.
Okay, we have our femtocell. This is currently disabled, and we're enabling it. We're disabling a plane mode from our phone, and it is connecting to a different cell nearby. It's actually our cell that has name, original name. We issue special commands to change this name and change the data on the phone. as you can see, we changed the date, the year of the phone, and actually we broke our WhatsApp application on the phone, and we sent the SMS to our phone that is bypassed integrity check, because we don't have any information about keys that are stored in our SIM card. We just bypassed it. What are implications of arbitrary SMSs? You can just spoof it, spoof the sender, but it's kind of dull. You can denial of service subscribers that are connecting to your FemtoCell. For example, on the right-hand side of the screen, you can see multiple SMSs that are sent in 1 minute. But the most interesting part is binary SMSs. Binary SMSs can be used to get the key from the SIM card. They were researched by Kostinol, by Alexander Zaitsev, with his co-speaker Sergei Gordeichik. And you can conduct all those attacks that were described with the power of the card reader by the air over 3G. So if you disable 2G in your phone, you are still not protected. And you can update files on your SIM card. I will return to it a bit later. What are authentication and integrity control in the GSM and 3G? In GSM, you have KC, just a ciphering key for its algorithms. And as a proof of authentication, it's just 4 bytes of data that is sent back to base station, and that's it. The phone doesn't authorize SIM card. The phone doesn't authorize base station. In the UMTS, there is different opportunities. For example, there are 2 keys. It's a ciphering key that is used for confidentiality, and integrity key for integrity. And as for proof of authentication, both for client and the base station, they both should know this key, and each packet should be signed by it. And actually, the rest is redundant. But there is a standard that it's maybe not well known. There are 4 opportunities to connecting for different cells. For example, if your SIM card does provide GSM AKA authentication, it can authenticate in UMTS by it. And as for GSM AKA in GSM networks, it was completely broken. There are different rainbow tables for creating man-in-the-middle attacks, for different denial of service attacks. Other two of modes are generally better. They are using protection against replay attacks. So you can't just take one information from the SIM card. You should possess it for a longer time. But there is an opportunity for GSM for UMTS. Yes, it's use GSM authentication. We sent only one random data to the SIM card. It receives 64-bit key, but we actually should obtain integrity key and ciphering key. And they come up with an idea. Why we just concatenate it and XOR it in some way? So we decreasing brute forcing resistance to 64 bits, and actually there is an opportunity to create rainbow tables for UMTS authentication and to break it in the matter of seconds or maybe in a matter of minutes. And there's an actual quote from the standard where they concatenating keys for ciphering key and XORing keys for integrity key. That's simple. What are possible attack vectors? If you want to connect someone to a 3G network, you can use Kraken to obtain KC for a given rand. This information is sufficient to connect any subscriber to the FemtoCell. You can use binary SMSs to obtain such information from the working cells over the air and without the proximity to the victim. Or you just use smart card. Maybe for those who will understand, this screen shows that all data that's sent to SIM card is just one authentication command, and actually it's a 3G connection. What are gateways? In a couple of days, we are going to issue a toolkit for these Huawei femto cells that creates your own UMTS in the box. You can have functional security gateway, so you can have management server, you can have HNB gateway, and it's actually sufficient to connect some or maybe all of your SIM cards to the femto cell and receive SMSs from it. It's a research ongoing, so from time to time this code will be updated and there will be different opportunities. For example, for now we are going to create voice over the 3G and create our own 3G network. We have reverse-friendly femto cell that is actually can be bought right now from the different Chinese marketplaces. And the knowledge, as we can humbly think about, that is not everything that good with the 3G networks because there are different opportunities to do things wrong and different opportunities to do things right. And actually, it's a kind of thing like Cosmocom BB that you can use by yourself to investigate these all opportunities. As for future plans, we are going to provide deep firmware analysis, including analysis of the digital signal processor. There are different opportunities for mobile phone fuzzing because ASN1 is the friendly interface, because there are different opportunities to send arbitrary amount of data inside this protocol. And we're going to have fun. We are thankful for our friends and colleagues and different guys from the internet who helped us in our research. For example, Kirill Nesterov or Benoit Michaud, who have awesome library for different 3G stuff. Thank you. Any questions?